In this video, we are going to see some mathematical concepts related to the Dirac equation. If you want to know all the details regarding this equation, you can check the course on quantum field theory. In this case, I'm just going to highlight some of the mathematical aspects of the equation. Let's start by writing down the equation. I, the imaginary unit, then we have the gamma matrices, gamma mu, del mu minus m applied to psi equal to 0. We are going to seek solutions in two different forms. These are the so-called plane wave solutions. Then, by using superposition, we can also find the most general solution. But let's start with psi plus of x, and in this case x is x0, x1, x2, x3. So we are really considering a 4-vector there, but I'm calling it x. And this function will be of the form u of p, where p is momentum, e to the minus I p dot x, and p dot x written in this form is simply equal to p mu x mu. You can check the course to get the details of this, as I said. Then I have psi minus of x, so I'm searching the solution also in this form, v of p e to the I p dot x, like this. And then if we substitute this expression, for example, psi plus, here, for psi, we are going to get the following equation. We are going to get I gamma mu, then we have minus I p mu, u of p, minus m u of p, times e to the minus I p dot x equal to 0, from which we find gamma mu p mu minus m u of p equal to 0. This is the first equation that we find, and if we use the so-called slash notation, we can rewrite gamma mu p mu simply as p slash. And similarly, we could also call del slash gamma mu del mu, like this. Therefore, the equation can be written like this: p slash minus m u of p equal to 0. Similarly, if we substitute the negative frequencies in the Dirac equation here, we are going to get something similar, and the equation that we find is the following. We get p slash plus m v of p equal to 0. Now we can also consider a rest frame, or if you want, a stationary frame, where momentum p mu, the form momentum, is equal to the mass and the 0 vector. So it means that it is stationary because momentum is equal to 0. With respect to this system, to this frame of reference, the particle is not moving. And since the equations are covariant, we can solve them in a rest frame and find the expressions for v of p and u of p, from which we can also generalize to a more general system. Now, if we consider p mu of this form, we can write this first equation as gamma 0 p0 minus m u of p equal to 0, and gamma 0 p0 plus m v of p equal to 0. But now we can call p0 simply as m, because this is the first component of momentum. By definition, we called it m. These equations become, therefore, gamma 0 minus 1, where this 1 is the identity matrix. It's a 4×4 matrix in this case, because gamma 0 is a matrix. Then we have u of m0 equal to 0, so I have substituted instead of p, we can write m0, because p, which is p mu, has this form. Then we have gamma 0 plus 1 v of m0, and this 0 here and here is a vector actually, so I could put also this arrow to denote that it is a vector, but it is not really important as long as we understand each other. And this is equal to 0, like this. For the gamma matrices, I can choose a particular representation where gamma 0 is equal to a 2 by 2 identity matrix that I will indicate like this, 1, and then here I have a 2 by 2 zero matrix, a 2 by 2 zero matrix, minus a 2 by 2 identity matrix like this, and then gamma I, where I can be either 1, 2, and 3, is equal to 0, sigma I denotes the ith Pauli matrix, then I have minus sigma I, 0, and this 0 and this 0 here are just 2 by 2 matrices. Why did I choose this representation? Well, this is a good choice because the gamma matrices must satisfy the so-called Clifford algebra. I have also shown this in a free video on YouTube, but this is also shown in my course on quantum field theory. So what can be shown is that these matrices should satisfy this relation. The anti-commutator gamma nu, which is equal by definition to gamma nu plus gamma nu, gamma mu. So we have a plus instead of a minus that we have in the commutator. So for the commutator we have a minus here, but for the anti-commutator we have a plus. And this is equal to 2 eta mu nu, where eta mu nu is the Lorentz metric. And these matrices also satisfy the relation gamma mu dagger. So we are taking the adjoint of gamma mu equal to gamma 0, gamma mu, gamma 0. This property can also be checked. In this representation, the equations that we found here have very simple solutions. We can see that there are two linearly independent solutions for each. In particular, you can check that gamma 0 minus the 4 by 4 identity matrix is equal to 0, 0, 0 minus 2 times the identity matrix, a 2 by 2 in this case identity matrix. And we have to solve gamma 0 minus 1 u of m0 equal to 0. This will give us two linearly independent solutions for u of m0. It can be easily seen from here because this matrix has a determinant equal to 0, but you can see that two rows are equal to 0. So we have two linearly independent solutions, and we can choose, for example, u1 of m0 equal to 1, 0, 0, 0, because u1 is a 4 by 1 vector. And then we have u2 of m0, 0, 1, 0, 0. We can choose it like this. Similarly, if we consider gamma 0 plus 1, we will get something like this. 2 times the 2 by 2 identity matrix, 0, 0, 0. And remember that these zeros here are actually 2 by 2 matrices. So when we consider gamma 0 plus 1 acting on v of m0 equal to 0, we also get two independent solutions for v1 and v2. And you can see that in this case, I have the last two rows equal to zeros. Therefore, these independent solutions in this case can be chosen like this. v1 of m0 will be 0, 0, 1, 0, and v2 of m0 will be 0, 0, 0, 1. Therefore, in general, for a generic system, we will have u sub r of p and v sub r of p, where r can be either 1 or 2, as we saw above. And these are the so-called spinors. They are 4-component spinors. We have u1, u2, v1, v2, and in general we can also rewrite them, for example, using another index, you are alpha of p, where this alpha indicates the components of the first spinor, because remember that this is a 4x1 vector as well as this one, so they have 4 components. And to explicitly write the 4 components, we can also use this notation where alpha is an index. As I said, we can take the values 0, 1, 2, 3, whereas r can take the values 1 and 2. And these values for r are related to the spin of this Dirac field. A general solution of the Dirac equation can be written in this form: psi of x is equal to the sum over the spin index. So we are summing over s, where s can take the values 1 and 2. Then we have an integral over momentum, d3p, over 2 pi cubed. This is simply a normalization factor. Then I have the mass of the particle divided by omega of p, where this differential together with the factor is something invariant. It can be proved to be invariant. I have done that in the course. You can check that if you want. Maybe in the future I will also add some videos on my YouTube channel related to how to prove the fact that this quantity here is an invariant. And by invariant I mean Lorentz invariant, because in quantum field theory we consider only Lorentz transformations. And omega of p can be written like this: it is the square root of m squared plus p squared, which is the magnitude squared of momentum. And we are using units such that u bar is equal to 1 and also the speed of light is equal to 1. So this is the Planck constant equal to 1 and the speed of light equal to 1 for the sake of convenience. And then here we have some operator c sub s of p, which multiplies the solution u sub s of p, the vector u sub s that we defined previously. The vector u sub s should satisfy this equation here, p slash minus m applied to u of p equal to 0. And then this multiplies the plane wave e to the minus I p dot x, and then we have plus ds dagger, in this case it is defined like this, ds dagger of p, v sub s of p e to the I p dot x, written in this form. And you can understand more about this, of course, by following the lectures on quantum field theory. Now, why do I say that c sub s and d sub s are operators? They are operators because the field should be quantized. And why should it be quantized? Well, in quantum field theory, we treat the field in the same manner as we treat position in quantum mechanics. And then we treat the so-called momentum density, which is called pi. We can call it pi psi, and it is a function of x and t, x vector and t time. So x vector and t time is what I called earlier x. And this momentum density can be obtained by using a Lagrangian. I will not get into the details of this. This will be, according to Lagrangian field theory, the derivative of the Lagrangian density with respect to d0 phi, so the derivative with respect to time of the field phi, and it can be shown that this is equal to I psi dagger of x, and then we treat pi sub psi as momentum in a similar fashion to how we treat momentum in quantum mechanics. And remember that in quantum mechanics we had something like this. We had a commutation relation between position, that in this case we have to consider as psi of t x, and momentum. In this case we have to put momentum density here, pi psi of t, the same time t, and then here we have a different x, so I can put x prime, and this will be equal to I, the complex unit times delta of x minus x prime. This is very similar to the relation that we have for the commutation between position and momentum. In that case, we have the complex unit multiplied by not the Dirac delta, but in that case we have a Kronecker delta. So for example, if we consider the position xj and pk of momentum, we have I times delta jk, for example. Okay, so there is a very apparent relationship between psi and position and pi psi and momentum. This is due to the formalism that we adopt in quantum field theory. Thanks to the formalism, we can try with some kind of intuition, imagination if you want. This is not so easy by any stretch of the imagination, but this is what physicists did in order to generalize classical field theory to quantum field theory. But anyway, in this case, for the Dirac field, it is not possible to construct a relationship like this, because this is not good for 1/2 spin particles. This is good for 0 spin particles, or bosons, but for fermions, the relationship should not be this one. It can be shown that the correct relationship should be with the anti-commutator instead of the commutator. So we have psi of tx pi psi of tx prime equal to I delta of x minus x prime, like this. And by using this relation, this commutation relation, it is possible to derive the commutation relations between these operators, Cs and ds dagger, because we know the expression for pi psi, which can be derived from the field theory, and these are just some of the mathematical expressions that we can write for the Dirac field, and more of this is explained in the quantum field theory course.